Hybridization. The valence bond theory explains well the formation of covalent bond by the overlap of orbital in case of simple molecule like hydrogen, fluorine, hydrogen fluoride, etc. Accordingly, the maximum number of covalent bonds which an atom can form equals the number of unpaired electrons present in its valence shell. But the theory does not explain how beryllium formed two covalent bonds or how boron shows. Trivalency. Carbon show tetravalency in spite of their electronic configuration. Example: beryllium dihydride, boron trifluoride, methane, carbon tetrachloride, etc. Beryllium 1s2, beryllium 1s2, 2s2, boron 1s2, 2s2, 2p1, carbon 1s2, 2s2, 2px1, 2p1. In order to explain the observed valency in this and such other compounds, a concept of hybridization was put forward. It was suggested that one electron in 2s orbital is promoted to the empty 2p orbital. Thus, in the excited state, beryllium, boron, and carbon have 2, 3, and 4 half pair orbitals respectively. Electronic configuration excited state: beryllium 1s2, 2s1, 2p1, boron is 1s2, 2s1, 2p2, carbon is 1s2, 2s1, 2p3. In the excited state, beryllium, boron, and carbon have 2 and 3 and 4 half-filled orbitals. So beryllium, boron, and carbon can form 2, 3, and 4 bonds respectively. This concept helps to understand how beryllium forms 2 bonds whereas boron and carbon form 3 and 4 bonds respectively. But it cannot explain how all bonds have same bond length and bond strength. For example, beryllium difluoride beryllium will use 1s and 1 half filled p orbital to overlap with a 2 half filled 2p orbital of fluorine. So in the molecule there will be 1 sp bonds and 1 pp bond, which will not be of equal strength. But actual both beryllium fluorine bonds are of the same strength. Similar situation is seen in boron trifluoride, boron trihydride, methane, carbon tetrachloro. In methane, all bonds are of equal strength, although the overlap are between s, px, py, pz orbital of carbon and s orbital of hydrogen. Experimentally, all carbon-hydrogen bond length, bond strength, and bond angle are found to be identical. This can be explained using another concept, hybridization in the valence bond theory. This concept helped to explain the observed structural property of many molecules. Hybridization refers to mixture of valence orbitals of same atoms and recasting them into equal number of new equivalent orbital hybrid orbitals. Steps considered in hybridization. First, formation of excited state. 2. Mixing and recasting of orbital. First, formation of the excited state. The paired electron in the ground state or uncoupled and one electron is promoted to the vacant orbital having slightly higher energy. Now total number of half-filled orbitals is equal to the valence of the element in the stable compound. In example, beryllium difluoride valence of beryllium is 2. In the excited state, one electron from 2s orbit is uncoupled and promoted to 2p orbitals. Ground state is 2s2, 2p. Excited state is 2s, 1 electron, 2p, 1 electron. Second, mixing and recasting. In this step, the two s and p orbital having slightly different energy mix with each other. Redistribution of electron density and energy takes place, and two new orbitals having exactly same shape and energy are formed. This new orbitals arrange themselves in new orbitals arrange themselves in space in such a way that there is maximum repulsion and minimum separation between them. So during formation of sp hybrid orbital, as in beryllium, the two sp hybrid orbitals are 180 degree. Condition for hybridization. First, orbital belonging to the same atom can participate in hybridization. Second, orbital having nearly same energy can undergo hybridization. So 2s and 2p orbital undergo hybridization, but 3s and 2p orbital do not. Characteristic feature of hybrid orbital. First, number of hybrid orbital formed is exactly the same as the participating atomic orbital. 2. They have same energy and shape. Third, hybrid orbital oriented in space in such a way that there is a maximum repulsion and thus are directional in nature. Fourth, the hybrid orbital are different in shapes from the participating atomic orbital, but they bear the characteristic of the atomic orbital from which they are derived. Fifth, each hybrid orbital can hold two electrons with opposite spin. Sixth, a hybrid orbital has two lobes on the two sides of the nucleus. One lobe is large and other is small. 7. Covalent bonds formed by hybrid orbitals are stronger than those formed by pure orbitals because the hybrid orbital has electron density concentrated on the side where the larger lobes and the other is small, allowing greater overlap of the orbital. 5.4.5 Type of hybridization and geometry of molecule. Different type of hybrid orbitals are obtained from the atomic orbital that participate in hybridization. SNP orbitals can hybridize to form the following hybrid orbitals. First sp3, second sp2, third is sp. First, sp3 hybridization. In this type, 1s and 3p orbital having comparable energy mix and recast to form 4 sp3 hybrid orbital. It should be remembered that s orbital is spherically symmetrical, while the px, p1, pz orbital have two lobes are directed along x, y, and z axis respectively. The four sp3 hybrid orbitals formed are equivalent in energy and shape. They have one large lobe and one small lobe. They are at an angle of 109 degree 28 minutes with each other in space and point towards the corner of tetrahedron methane, ammonia, water example, where the orbital on central atom undergo sp3 hybridizations. Formation of sp3 hybrid orbital. Formation of methane molecule. Ground state electronic configuration of carbon is 1s2, 2s2, 2px1, 2py1, 2pz0. In order to form four equivalent bonds with hydrogen, the 2s and 2p orbital undergo hybridizations. Electronic configuration of carbon 1s, 2s, 2p ground state 1s 2 electron, 2s 2 electron, 2p 2 electron excited state sp3 hybrid orbital 4 sp3 hybrid orbitals. One electron from the 2s orbital of carbon atom is excited to 2p0 orbital. Then the 4 orbital 2s, px and py and pz mix and recast to form 4 new sp3 hybrid orbitals having same shape and equal energy. They are maximum apart and have tetrahedral geometry. Each hybrid orbital contains one unpaired electron. Each of these sp3 hybrid orbitals with one electron overlap axially with the 1s orbital of hydrogen atom to form one CH one CH sigma bond. Thus in methane molecule we have 4 CH bond formed by sp3s overlap. 1s orbital H sp3 hybrid orbital of carbon and methane. sp2 hybridization. This hybridization involves mixing of 1s and 2p orbital to give 3 sp2 hybrid orbital of same energy and shape. The three orbitals are maximum apart and oriented at angle of 120 degree and are in one plane. The third p orbital does not participate in hybridization and remain at right angle to the plane of the sp2 hybrid orbital FBF3's ethene molecule. Example of sp2 hybridization 2s 2px 2ps sp2 hybridize shown together. Formation of sp2 hybrid orbital. Formation of ethene molecule. This molecule contains two carbon atoms each bound to hydrogen. Each carbon atom undergoes sp2 hybridization. When s orbital and 2p orbital can on carbon hybridize to form 3 sp2 hybrid orbital of equal energy and symmetry. Two sp2 hybrid orbitals overlap axially. Two s orbital of hydrogen to form sp2s sigma bond. The unhybridized p orbital on the two carbon atom overlap laterally to form a lateral pi overlap. The C2H4 molecule has 4 sp2s sigma bond, 1 sp2 sigma bond, 1 pp pi bond. Electronic configuration of carbon. Ground state 1s 2s 2p. So 1s2 2s2 2p2. Excited state will be 1s2 2s 1 2p 3 sp2 hybridize. Orbital p orbitals. Formation of boron trifluoride BF3 molecules. First, need of hybridization. Observed valency of boron in BF3 is 3 and its geometry is triangular planar, which can be explained on the basis of sp2 hybridizations.